Okay, now the good news is that you already know how to solve alpha decay. So all we have to do is like say a few things about it, and then we'll show it. But the way to solve alpha decay is that we're going to compare the things that it flies apart into to the things it came from, and the rate of energy will be manifested as a loss of mass, and that loss of mass times 931.5 will be our energy of decay. So it's really not very hard. I like this chapter because we go from non-causality, quantum randomness, non-determinism to adding numbers up and subtracting. It has a certain concreteness to it, even though it's really bizarre that we're turning mass into energy. That's bizarre. And even if we have antimatter and we don't seem to be disturbed by the fact that I just said here's a positron, okay? That's sort of disturbing, but it's only minorly disturbing, right? So I think you have this example, don't you, in your note guide? So in that, on the sheet, on the note guide sheet, okay? On this note guide sheet, find this little space here. I'll show you the calculation, okay? The calculation will be this. We'll find these masses. Now, where do these masses come from?
Appendix F.
Yeah, they come from, is it Appendix F?
Yeah.
It's in the back of your book on page 1064. Page 1064. You go back there and you look at all of the data. Oh, I've got it tabbed in my book here. Okay, this is data frozen in like the 80s or something like that, late 90s. Okay, and so obviously if you were doing careful work, if you were a researcher, you'd go to the South Korean site, or you could just go there right now and get the data. Just keep in mind that you're going to be slightly off from what the book is because these values haven't been updated and they're basing their answers on the book. But you shouldn't be too far off if you just use the values from the website, right? So you look these guys up, you look this one up, and then for an alpha particle, what you use is the mass of a helium atom with all of its electrons, and that's not a problem because I'll show you why in just a sec. Okay, so alpha.
What is that little dash right?
Oh, just that's like a right arrow. Only I was too lazy to like put an arrow in there, right? So let's zoom in on this so that the calculation is a little more visible, right? So alpha energy. All I'm going to do is I'm going to take this side here, 232.037131, and I'm going to go minus the right side of the equation, which is 228.028716 plus 4.002602. That's the one I don't have to look up because I've memorized it. This is a 4. Yeah. And I get that the right side mass is less than the left side mass by... And just for fun, I'm going to itemize this right side. I'm going to go 228.02728, whoops, 716 plus, bless you. You got to do a snort laugh, you know. Okay, this is the mass I get. Is this less than this mass?
Yeah.
Yes, okay, so the question is, where did the mass go?
Energy.
Turned into energy, right? So if the right side has less mass than the left side, if the things you're turning into involve a release of mass, it's also a release of energy. So this is something that's called exoergic, right? Right? Or exothermal is what we talked about in the chemistry, right? Just exo means it goes outward, right? If it requires energy, it's not something that happens spontaneously. Those things are called endoergic. I'm not going to write it up there, or endothermic in chemistry, right? Endoergic means that it requires the input of energy. That's what we have particle accelerators for. That's what we're using them for, is to make those things happen, like creating the top quark or something like that, right? It requires a ton of energy, the Higgs boson, right? Okay, these things require a ton of energy, and our colliders provide that energy, right? So when I subtract this, I get that the mass went down by 0.005813 U's, right? And that's the number I'm going to use to calculate the energy, right? right? Remember, this is MeV per U, and so times. Sometimes I think that mass spectroscopists feel used. Very obscure joke. Thank you. Yeah, they feel.
So that's the energy loss.
Yeah, so this is called. Nobody will argue with you if you say this is the energy of the decay, because that is the energy released. We can tell that by looking at the parts and everything like that, right? That's how much mass got converted into energy, and that's the energy it represents. People might quibble with you a little bit if you say that's the energy, the kinetic energy of the alpha particle. And the reason that they're going to quibble with you is that if energy is conserved and you've got this particle flying this way, doesn't the nucleus have to recoil a little bit? Yeah. Right? But just like the cannon, when we fired off the physics cannon last year, the cannonball went that way, but the cannon moved in a more stately fashion backwards, correct? Yeah. Right? Not enough speed to like rip the little wolf into little pieces and leave the little footpads behind, right? But enough speed that we could measure. I know that Thompson's like chafing about that. But here's the deal. Remember that kinetic energy is 1 FmV squared. And so since this one's got so much more velocity, it's basically its kinetic energy just eclipses this. This is like a fraction of a percent of the total energy. So you really, it mostly is the kinetic energy of these guys. When you detect them, they've got this energy pretty much spot on. Yeah. The second thing you should know is that this energy is discrete. That is, when you detect these alpha particles, you can identify this particular decay by that energy. It's spot on. When you look at this, right, it's the detector data is always intensity versus energy, right? And then there's always like, the energy of decay of the positron, and then right, and then there's the, here's this guy out here. Right? It's going to be this little spike, just like a spectral line. You can detect these things, only their particle energy is not light. But you can detect them, and if you've got a good enough detector, it's this nice little spiky thing. And all the other decays that are going on have their own energy, and you can see them. It's like a little forest of spikes, which is kind of cool.
Is there any, Mr. Murray, is there any does it spike at given intervals, kind of like the
Well, okay, yeah, it can actually, some of that energy can actually be given to a subsequent gamma ray, right? So that's also possible. It's a little bit more complicated than that. But it's, for sure, it's discrete lines. This is a discrete spectrum. Not discrete as in, well, anyway, discrete as in particular lines. I was going to try to make some funny joke, but I figure I shouldn't make fun of Mayor Adams on YouTube. So. Mayor of Portland. All right. So try this one. This is berkelium alpha decays into americium. Yeah.